Nothing to do with that.
Is Pledging already like number 11 or is it
Okay, we started at number 11.
Energy, material, nutrient, water, organic. Yeah, we're starting on number 11, children. Okay, here we go. Yesterday, did we talk about the different layers of the earth?
Yes.
Yesterday, excuse me, did we talk about the composition of the whole earth, the crust, and the core? Did we talk about how it's not a perfect blend? And how it's not a perfect layering? Because of? Okay, these forces.
You did tell us the truth.
We stopped here. This cycle includes 3 things that scramble the eggs, that shuffle the deck, that blend the ingredients. This set of vocabulary explains how different ingredients of the Earth's crust will dissolve, transport, and deposit. Those are the 3 buzzwords we want to find. Where they are dissolving, where they're being transported, and where they are being deposited to make uneven distribution of ingredients, exceptions to the density stack. Anybody want to ask me a vocab question on this slide? This is an awkward moment for me because if I was going to read all these, I'd waste a half period, and most of you have heard this. On the other hand, a lot of you were absent that day in the 7th grade, and you might need these, and it's not your fault, and I'm happy to help you, but you'll have to ask me, please. Yes?
For the warm-up and the weathering, are you going to get that later?
Weathering I will discuss. What else? Last call. Please look at these and make sure you don't want to ask me.
What's deformation?
That's when sedimentary rock is physically changed in shape. Metamorphism is when it's changed in chemical bonding and structure and composition. What else? Oh, you can imagine if you had layers of Play-Doh. make clean layers, and then you like ball it up, that'd be deformation. It's still distinct layers, but they're not going to line up anymore and stuff like that. What else? One thing I'd like to point out, your body, if we were to describe it with one of these diagrams, would have a circulatory system and a lymphatic system, a digestive system, an endocrine system, your eating, farting, pooping system. And that would make a whole bunch of arrows like this. That doesn't mean it's all one cycle, right? Please don't look at this as if it is 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, because it's not. Like your body, these systems are sometimes sequential, sometimes parallel, sometimes contradictory. These are not chronologically sequential. Is that clear? First, tectonics. That crust is not still. That crust keeps changing. Because the tectonics of the earth, that crust is broken up into little pieces, and those little pieces are moving. You should know the different type of plate boundaries. What do you call it when they go like this? When they go like this? When they go like this? Transform. Anybody know why it's called a fault? Because it explains errors on maps. So did you guys hear that there was an earthquake in Chile a couple days ago? Big one, 8.2. Yeah, really big one. So apparently, the measurements. I mean, I haven't seen it. They're probably published. I just haven't seen yet the measurements. But do you know that about 11 or 12 years ago there was a similarly large earthquake in Chile? Mm-hmm. It happened when you were 6 or 7 or something. There was like this one really big ass earthquake down there. Just the same as this one, 8.4, 8.5, something really, really big. The capital city moved 11 feet. Because of the previous one. I haven't heard how much it moved in this one. But GPS readings would be like, whoa, my house is supposed to be over there. And the city moved like a little bit north, a little bit west, and a little bit up. This is why it's called faults. They rub against each other. Cool map. If you want to check out that map sometime. You can see here where the boundaries are spreading. All spreading boundaries are at the bottom of the earth with one exception. Anybody know which is the only surface spreading boundary?
The Mariana Trench.
Iceland, which is why they produce all that geothermal energy. You'll notice that this fault goes right smack dab through the middle of Iceland. Very unique geology in Iceland. So they're spreading, wherever they're new, it's thin. Hasn't gained a lot of material yet, so new plates are like a crack in a scab, where they separate from each other and juice comes out between them and then dries up. So they make these really neat patterns, little underwater mountain ranges, because when they spread away from each other, the juice comes out over the top and then cools, and then spreads and the juice comes out and cools. So they tend to be these like growing mountain ranges. All the tallest mountains in the world are underwater. You guys know that? Yeah. They haven't been weathered yet. As those plates slam into each other, they pile up on each other, become thicker, and thus float on the magma higher, so they're out of the water. The thin ones plus the water have roughly the same net mass as the thick ones. It's all floating on a layer of magma that's roughly the same depth. So the thick ones are the continental plates. The thin ones are the underwater plates. That's why there's all the water piled up on top of them, because they're light enough to sink with. What else? If you want, you can look at these and see where the arrows are moving them. So you can tell where they're colliding, the ring of fire, for example, and where they are spreading, the bottoms of the oceans. Check out our cool little quirk. I'll show it to you on the screen, actually.
Is that why there's the Gulf of Mexico? Not the Gulf of Mexico, but like Baja?
Yeah. Cool little quirk. We happen to be right here, where these are moving past each other. That's the San Andreas Fault right there. And you might know that this little sliver of the map, this piece, which includes Baja, is moving that way, while the rest of your motherland is moving that way.
So we're going to split up.
So any day now, this chunk of dirt plus Baja will find itself drifting out to the Pacific. Just a couple minutes now.
Oh, I feel it.
Make it stop. Slow down.
Oh, we're good. Oh, I feel it.
Interesting thing that happens is because of all this plates plus lava plus friction plus layering and melting, plate boundaries tend to aggregate metals. Metals will melt in all that magma, and they will cool differentially. So metals are organized by that melting and density and cooling process into largely uniform deposits near mountain ranges and volcanoes. So tectonic regions where you have igneous process where rock melts and cools will aggregate metal deposits. Do you guys know the story of the Hawaiian Islands? There's a hot spot and the plate is moving over it. As that plate moves over the hot spot, occasionally little burps of lava will break through that crust and make one of the islands, and then the plate keeps moving and another burp will make another island. So where you see that chain, the archipelago of Hawaiian Islands, that shows you the history of where the Pacific plate has moved over that hot spot. Yeah, the next Hawaiian island already has a name. It's got about, I think, 300 or 600 feet to go before it breaks the surface. Any day now.
Actually,
No, I mean, it probably would be a very long time. So volcanic activity is hard to predict, and you don't know how big the eruption would be in that underwater seamount, before it surfaces. But it already has a name. Something like L. Anybody know the name? Thank you. There it is. Yes. Peak of creativity in the back. Okay. Next. Another way that we make rocks is through the sedimentary process. But sedimentation has a few interesting quirks. For one thing, you take all the little bits of sand and you let them fuse into rock again. That's how we make sedimentary rock like the ones where we live. But there's another funny thing that happens with sediment. They're called placer deposits. New vocab for you.
Which number is this?
All number 11.
what time did this period start?
I don't know. In placer deposits, you get separated aggregations by density. By now you should know a pattern because I've said it a billion times this year. Depending on the speed of water, moving streams and rivers can carry things of different size. Fast-moving water can carry houses, school buses, boulders even. And as that water slows down, the heaviest things will settle. If it gets slower, slightly smaller things will settle. When the water is barely moving, it'll still have a little bit of suspended sediment. When the water is perfectly still, it gets crystal clear because even the finest sediment will settle. Agreed? So you have boulders tumbling around up high, rocks only being moved, cobbles being moved, gravel only being moved, and the only thing carried when you get near the ocean is sand. That's how all the sand gets to make our beaches. So up on the mountains you have weathering, where rocks are being broken apart. We'll come back to weathering next. And as that water slows down, you get what are called placer deposits. In this gradient of density, you might find that the water hit a slowing spot and one particular density fell out of suspension. Like all the nuggets of gold, for example. See, if you had a streak of gold in this mountain, it would be weathered by the rainfall, broken up into smaller pieces by the tumbling down the river, and eventually where the water slows down to just that critical speed, that shift in speed, that slowing, means that all the gold that was moving will go, stop moving. Placer deposits.
You're just waiting for it.
Sedimentation is, first of all, how we get sedimentary rocks like that one. And second of all, how we sort elements based on their density in placer deposits. Next is the weathering. What are the two types of weathering? Wind and rain. There are other factors which cause weathering, but those are examples of the two categories, the two types. Yeah, chemical and mechanical, or chemical and physical. You can either break up rock by dissolving the bonds, that would be chemical, because all rain is acidic and some of it is very acidic. We call weathering by the liquid of the rain, that's chemical weathering. Physical or mechanical weathering is when the rock is broken into smaller pieces by impact or other forces. Anybody know what weathered this rock? This is wind pocketing. So the rock has weaknesses, and basically wind-blown sand causes all of these. How many of you, a lot of you are recognized from the lizard's mouth cleanup, right? So the mouth and many of those rocks, those were pocketed by wind erosion. That's sand blasting, wind-blown sand. What? No, I don't know this picture.
Wait, so wind counts as physical?
Wind is physical. If you look closely at many types of rock, they're either sand glued together by chemical bonds. Those would dissolve when the chemistry changes. That would be chemical. Or there are large crystals of mineral that were fused together in the metamorphic or the igneous process. Those likewise can either be broken apart by sandblasting or dissolved away from each other by chemical weathering. There is one other type of weathering that I wanted to talk about. This is one of those two. When you look at this, it's called exfoliated granite. Anybody know what causes the granite to fall apart like this? What? Nope. Nope. It's a uniform
Your mom walked around.
rock type.
Oh, when like water gets in cracks and then it freezes.
Yeah, what Graham just said. Graham, try it.
When water gets in between cracks and then freezes and thaws.
They're called freeze-thaw cycles, or freeze-thaw cycling. It's a type of mechanical weathering. You have a little weakness in the rock, water gets into it. When that water freezes, it will expand. By expanding, it pushes the layers away from each other, and it's like a very slow-motion jackhammer. Every freeze is like one strike of the jackhammer. Over thousands and millions of years, you can basically peel off successive layers of El Cap and Half Dome and giant monoliths of granite. If you look right back there, you see a little 3/4 inch gap between those two gray filing cabinets. Imagine if I could fill that with water and then freeze it. I could grow that by like a 32nd of an inch or so. After a few years, that might peel off entirely and tumble down. The most dangerous time to climb in Yosemite is definitely in the spring, when all that ice thaws and those flakes that were separated are released by the melting. My homie was in Yosemite many, many years ago. I can tell you the year. In the year 2000, in the spring of the year 2000. And he's on the phone right across the street from Camp 4, and he's like, oh, blah, 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 blah. We're like making some plans. I was here in Santa Barbara planning to go visit him right at the start of summer. And all of a sudden, I thought there was like a really giant car accident. I heard like... And he's like, hold on. I was like, Don, buddy, Don, what's going on? What happened? You okay? What's going on, Don? And I just hear like people screaming and like brakes, sirens. And there had been this really giant rock fall on El Cap, right here. The rock fall was, like, you can't quite see it in either of these photos. I probably have another photo up here where you can see where it happened. But this giant layer basically exfoliated off. And then as that ice started to melt, there wasn't enough bond to hold it up anymore. And so you had separated a giant shield of granite that was just held on by ice contact. As the ice starts to trickle away and melt, the thing just gets heavy enough to go, it slips off. And it shot like boulders, like big school bus boulders all across the road. And like it was a really devastating rock fall. I think in the end, someone died of a heart attack, and all the injuries were caused by cars that came to a halt as the rocks were falling across the road. So, like, people would stop, and people come around and turn at high speed and just, like, rear-end each other. So there was a lot of car accidents afterward, but nobody got hurt by falling rock that I know of.
The rockers, the troublemakers.
Yeah. Okay, so anyway, that's another type of mechanical. Another way we organize stuff is some elements will dissolve into water, and once they've dissolved into the water, they'll be carried around until the water leaves them behind. If the water can't escape, it must evaporate. These are called basins or sinks, where water spills in, then cannot pour out, so it just evaporates up into the air, leaving behind these giant salt flats. So evaporation makes deposits of minerals which dissolve in water.
Evaporation is a type of weather.
Evaporation is not, we're done with weathering. This is one of the things that causes unusual shuffling of the ingredients. Anything which dissolves into water but doesn't evaporate will make these wherever the water is left, wherever the water is pooled up. And last, I want to talk about the story of this type of rock. This is an example of biological processes, but it's a much more interesting story.
Got a mushroom.
Too small.
What? It kind of died on the way here.
Yeah, I know, it's okay. It's never finance. See you guys. Go.
Can I use your microwave?
No. Anybody know what type of rock that is?
Thailand.
Thailand is right.
Big one. Big one.
Rock climbers had to learn this one. This is highly sought after by rock climbers. Because it makes these really unique semi-phallic pillars that have really spectacular weathering. So they have very, very unusual types of climbing maneuvers. This is the most athletic and coincidentally the most challenging, the highest grades in rock climbing are all on this type of rock. Somebody said something very close to it. It's very close. Chemically the same as marble. This is
Marble's brother.
This is limestone. And I said, this is made by a biological process. Anybody know which biological process makes these?
Reproduction. It's calcium carbonate.
It's calcium carbonate.
It's just like seashells and sand and
Yeah.
coral.
So here comes the story now. Because here comes a blend of many forces. Wow, the school district is calling. I have to answer this. This is Jose. Hi, Beth. What's up? I teach all the periods, and I have a pep rally, so I have a unique schedule that's sneaking up on me. Hold on a second. Anybody know when lunch is today? I'm sure that's not true. Beth, my best bet would be.
It's at 12:30.
You sure?
Yeah.
Great. So sometime between 12:30 and 1:10 is the best chance, but I'll be meeting with a student also, so I'll have to make it kind of fast. I won't be down there until lunch, so just let me know when you get here, and I can go down there and open it for you, and you can help yourself to whatever you'd like. Yeah, no problem, Ben. Okay, bye. Here comes the neat story of these limestone towers. We only have 5 minutes. I really got to finish this. Calcium builds up in rocks, but carbon does not. You know that carbon makes hydrocarbons, makes organic compounds, makes CO2 in the atmosphere. But here comes the funny story of limestone. The calcium weathers out of rocks because of chemical weathering. Calcium will dissolve into water, calcium ions. Carbon, usually from the atmosphere, will dissolve into the water as carbonate ions. And in the ocean, calcium and carbonate are put together to make calcium carbonate by anything which builds a shell. This is the biological process that creates the chemical compound, calcium carbonate. Now, the shells are not limestone. Instead, things that build a shell and coral are chipped apart into little pieces by wave action, worms, and fish that can break them, making a type of sand called puka sand. Have any of you been to the tropics and seen that lighter, crumbly sand. It's called puka sand. If you put it in a bucket, it's not that heavy, but it's much more coarse than ours. You know what I'm talking about? People make like puka bracelets and puka necklaces. Many decades ago, those were popular among surfers because of the Hawaiian reference. Yeah, like shells, little square pieces of shell with a hole drilled in the middle. That type of sand makes a sedimentary deposit in the bottom of the ocean that gets buried by other sediments. It is deformed and metamorphosed by pressure into layers of limestone. Those layers of limestone are uplifted where the plates collide. And then, weathering, chemical weathering, because acid dissolves limestone, once they've been exposed to the surface, the chemical weathering will shape them into those unique limestone towers. Notice this is basically a combination of almost all the terms I used before. This is what we mean by the unusual geological forces that shuffle the deck. There would be no other way to make these limestone towers, except to go through that calcium dissolving out of one sort of parent material and the carbonate coming from the atmosphere into the ocean, where the biological process makes the calcium carbonate, which is broken up into smaller pieces by another ecological force, which is then sedimentary, which is then metamorphosed, which is then uplifted, and which is then weathered into these shapes. BT dubs, these dissolve very quickly. All rain is slightly acidic. And so on limestone, if you touch it when it's wet, literally like a good rubbing the water off will make it slightly thinner right there. Coincidentally, because limestone is so fragile, there's this really hot topic among climbers today, trying to figure out which type of metal bolts to use to protect the rock, because the chemistry of the drilling, bolting, and erosion makes limestone especially unsafe. If you ever had the opportunity to climb in Vietnam, Cambodia, Thailand, Laos, you got to make really damn certain that those bolts are especially secure. What would work in sandstone and granite will not work in these types of rock.
Have you climbed there?
I've not.
You hope you-
It's not really my style, but maybe someday. Okay, I'm sorry, but we're almost out of time. So I think I'm going to stop here.